Hey everyone, welcome back to my channel. So in today's video, we will talk about how you can build your own neural network using PyTorch. In the last video, we had a very brief introduction to deep learning where we understood what is an activation layer and how you can, represent a neural network. So I thought in this video, it will be better, it will give you a better understanding if we start coding up our own neural networks and start seeing the benefits of using activation layers to improve performance on certain tasks, right? So let's get started. So this will be mostly a coding based session only. So we have a code written which will show a comparison of performance of a task versus on a linear classification or a linear classifier versus a non-linear classifier, right? So we'll see both the performances. So for example, let's see first here that we import torch. So this is written in PyTorch. So we import the necessary libraries. Then it is again the same task which we have done earlier in linear classification, and if you have not seen that video, please see that video so you'll get to know from where we have started our journey. So the link of that video is in the I button above, and see that video and see what we have done there, and then it will start making sense to you for here also. Even if you don't want to see that video, I'll just give you a very brief high level introduction of what we are trying to do here. So what we have done is basically we have plotted points between 0 to 1, right? And whatever points are inside the circle of radius 1 are colored as yellow points, and whatever are outside those circle are colored as purple points, right? So that is our data set. What we want to do is we want to learn a classifier which is able to learn this boundary, right? Okay. So then few of the functions that we want to decide that will be helpful for our models. So first is the accuracy function. So accuracy, we all know, is the how accurate your prediction is. So prediction label and the comparison between the prediction label and the points in the circle, which is the ground truth, becomes your accuracy. Then this is a show function. Show function is nothing, just to print whatever predictions you have done so that we can visually inspect and see how well our model is performing. Then the loss function, we all know how do we calculate a loss. So this is the implementation of that simple loss function. And then comes a linear layer, right? So till now we were hard coding or hand coding all these things in our models, but now we will start making use of libraries or extensions that PyTorch provide to build our models, because once the models start getting complex, writing everything by hand or calculating everything by hand is very tedious and is very prone to error, right? So this is the first class. So I've created one class which is called a linear class. This is a linear layer that I want to use in my code, and in the init function we see that there are two parameters, which is the weight and the biases, and we all know that both the parameters are what are needed for any classification, right? For a linear classification. So a linear layer has two parameters, which is the weight and the biases. And then the forward function is nothing but x multiplied by weight plus bias. This is the equation that we have been talking about all along. So this is the linear regression equation, a linear classification equation. Then comes your linear classifier. So what does a linear classifier has? It extends from the torch NN module. Then it defines an init function. Init function, it's simply single layer because it's a linear classifier. So it's a single layer, linear layer classifier. And the forward function is nothing but just an output of the linear layer and then pass through a sigmoid function, right? And sigmoid, we discussed that why we use sigmoid to bring the output between 0 to 1, right? Then what I have printed here is show x in circle. So this is just how just to show how you can visualize your input data set. So this is how your data set is, and this is the circle which we are trying to learn here. So let's start by using our linear classifier. Okay, so in linear classifier, what we have, we initialize the linear classifier and we pass the parameter as 2 because that is what our input, that is the number of dimensions for our input, which is 2. And then we start the training process, right? So we will run this code for 10,000 iterations. The first step that we do is we call classifier x and we classify a particular point. So x is a point and we classify that particular point. Then we see the predictions of y, right? So what y py is giving is the probability, and then we convert it into predictions by saying that if the probability is greater than 0.5, then it is 1, otherwise it is 0, right? So we convert the probabilities into predictions, and then we pass the predictions into the loss function, right? So then we calculate the loss. Loss dot backward is used to calculate or do backward propagation or gradient descent, right? So gradient descent also we have discussed in detail. Again, the video for that you can find in the I button. So instead of doing that by hand in this video, or going forward we'll not do it by hand, we'll just call the backward function, and backward function for you will do the gradient descent, calculate the gradients for you, right? You don't have to do anything. It will not do gradient descent, it will just calculate the gradients, and then you have to update your parameters based on the calculated gradient. Okay, now what we have to do, we have the gradient calculated, so now we have to update our parameters, right? So how we updated the parameters, we usually do like w new is equals to w old minus alpha into your gradient. Something similar we are doing here, but we are not doing it per parameter. We are just looping through the classifier parameters, which we know are two parameters, which is the w and b. We loop through those parameters and we update the parameters by multiplying 0.5, which is the learning rate here, into the gradient value, right? So exactly similar to what we were doing earlier, but this is here we are not writing those parameters explicitly, rather we are just looping through the classifier parameters and updating this gradient, right? And then finally we call the grad 0 function. So why do we need to call this function is because the backward function actually does not clears out your gradient after every iteration, right? It keeps on adding the gradient to the to the calculated gradient. It keeps on adding it to the existing value and does not start from beginning. And if you do not zero it out, then you will basically in the next iteration you will take into consideration the gradient of that particular iteration and the iteration previous to that, right? So that is not what we want to do. We want to take the gradient of every iteration into consideration, and that is why we call a function to zero out the gradient after that has been used for particular variable. And then after your every 1000 iterations, I am printing the iteration number and what is the accuracy that we have reached, right? So this is something very similar to what we have already seen, right? Linear classifier, we have been talking from the last 5-6 videos, we have been talking about linear classification, linear regression and all those things also. So by now it is a very simplistic code and should not be difficult to understand, right? So let us try to run this thing. So we see that the maximum accuracy we have reached in 1000 iterations only, and then the accuracy stays same. It stays at 96% because that is the maximum that you are able to learn with a linear classifier. A linear classifier cannot learn an arc, therefore it will never be able to achieve a accuracy of 100%. But here, since it's just a linear line, it is not able to even classify a few of the points that are placed on the boundary of this arc, right? And that is why the accuracy is stuck at 96%, and that is the best that a linear model can do on this task, right? Because what you are trying to estimate is an arc, which is a 2-degree function, but a linear is a single degree function. So never a single degree function will be able to mimic or predict the behavior of or map the behavior of a higher order function. Okay, so this is again what we have seen earlier. Now comes the interesting part where we try to build our first neural network and define a non-linear classifier. So we discussed in the previous video, in an introduction video, that even by adding just one activation layer between two linear layers, theoretically it gives you the ability to predict any complex continuous function, right? So we will see that in action here, right? So again, the definition part is same, that I define a non-linear classifier, which is a torch NN module, extends from torch NN module. Then I define the init function. Then we have your first linear layer. So it takes the input dimension as 2 and has the output dimension of 100. This is again something that you can keep based on your training requirements. Then we have one activation layer, which is a ReLU activation. And then finally a second linear layer, which is again a dimension 100, right? Now, for your forward function, we pass the input x through all these layers. So first we pass it from linear 1 layer, then the output of that is passed to the activation layer, and then the output of that is passed to the linear 2 layer, and then finally it is basically sort of passed to the sigmoid function. We calculate the sigmoid. So this is your how you can define a nonlinear classifier. And if I run this, so this is how your classifier is, right? It is a simple 3-layer network, which is out of which 2 are linear layers and 1 is an activation layer, right? And this is what we saw in that earlier video also, how you can create a very simple non-linear network by just adding one activation layer in between 2 linear layers, because if you just combine 2 linear layers, the result is just a linear layer, right? So you have to add an activation between 2 linear layers. So rest everything with respect to training your classifier stays the same, and that is why I did not use, or we did not use, W and B to update parameters, because then here we would have to change that. Here we will directly use the classifier parameters, and the rest of the part of the code remains exactly same. So now one thing to note here is that I have reduced the iterations by half, right? I'll just train this for 5,000 iterations, and you'll see how even in less number of iterations it is able to perform better than the linear classifier, right? So let's start training, and we see that even just after 1,000 iterations, the accuracy has reached to 98%, and by 2,000 iterations the accuracy has reached to 99%. Like this is the sort of performing much better than your linear model. And here we see that it is able to learn how to predict the curve of this function, right? How to predict or map out the curve of this function, which is a circle of radius 1, right? So it is able to learn those things just by adding one single non-linear layer. And why it is able to do that? Because this allows it more flexibility, or allows it to map more complex functions by introducing non-linearity in the network, right? So you can use this code, you can use this training code for training your own neural networks also. I'll attach the link to this in the description, and you can experiment by adding more layers here. You can experiment by trying out different activation functions, changing out the output dimension of the first linear layer, and you can try all sorts of things, and you can see how you can even further improve and see if you can reach to 100%, right? If that is possible, you can reach to 100% accuracy. And you can play with making this model very deep, and just enter into the arena of deep neural networks, and you can do all sorts of things and try it out. So that is it for this video. I just wanted to show how we can as a real example, as a comparison scenario, how you can see the benefits or the difference in the performance of a linear model versus a non-linear model, and understand how important it is to build models or build non-linear models to solve more complex or more nuanced tasks, because linear models have their own capabilities and they cannot perform beyond a certain capability. So thank you so much for watching this video. Please like, share and subscribe to this video, and follow, press the bell notification icon, because now we are entering into a very interesting area of deep learning, and all the next videos will be very interesting to you. Thank you so much.